Okay, not actually how the eye perceives color. Color is definitely a theme of this presentation. It goes along with your notes entitled, "Here's Looking at You, Kid." That phrase is a line pilfered from a famous film called Casablanca. I haven't seen the film, but apparently quite the classic of Humphrey Bogart, Ingrid Bergman, and Paul Heinried. Alright, so a couple of blanks to fill in here. Key terms that will run throughout this entire presentation. Anything which emits or gives off waves or particles is said to radiate. Radiate. Stars emit, give off, a broad spectrum of electromagnetic radiation. Radiation often has people thinking of very negative things, where radiation is absolutely common, and radiation means to give off waves or particles. As I'm talking right now, I'm giving off particles, sound waves, and hopefully tomorrow I'll return to class and I won't have a third head, I won't be glowing, I won't infect you with radiation. Radiation, very broad term, to give off waves or particles. If you turn to someone near you and say, "Hi, how are you?" you've just radiated them. People tend to think of the most extreme, fatal situations with radiation and not respect the fact that there's an enormous amount of less detrimental forms of radiation. So there is a wide range of energy-carrying waves which make up the EM spectrum, electromagnetic, part electricity, part magnetism. You're probably familiar from earlier science classes. This is the EM spectrum. And as we look at this EM spectrum, this is the portion that you and I are able to perceive with our eyes. We can perceive other portions with our skin, like infrared radiation here, heat radiation. You step outside, you can feel the sun's warmth on you, so you can perceive the radiation that way. These high energy gamma waves, very short wavelengths, high energy, high frequencies. These are the ones that can be the most devastating for humans, but there are still good attributes that we can use gamma radiation for. So stars will emit frequencies within this EM spectrum. The way you and I perceive electromagnetic radiation with our eyes is through color. Red is the lowest energy, longest wavelength, and we tend not to refer to the term violet. We usually use the extremes of red and blue. So your blue is your higher frequencies, high energy, lower energies. And the electromagnetic spectrum is something we want to focus on because everything we've shown you so far about astronomy has just been in this visible light area. Look up at the dots in the night sky. There's so much more to behold of the cosmos if we think about other frequencies we don't perceive directly with our eyes. Again, you and I perceive the visible portion of the spectrum between this 400 and 700 nanometer range. A nanometer is a billionth of a meter. So take a meter, chop it into a billion pieces. One of those pieces would be called a nanometer. And we perceive the visible light in terms of color. Sunlight, an example of what we would call white light. Now I know as kids you want to color the sun, you would grab the yellow crayon, but the light in hallways, rooms, we would refer to as white light. When a ray of sunlight is diffracted, so this means to spread out. I'm going to show you some examples of diffraction here. This is diffraction grating. It's a piece of plastic, it's highly polished, and it has lines etched into it. So a laser etches lines into it. This particular one, as they come in all different varieties, has 600 laser lines etched into it, or lines that have been etched by a laser. So 600 lines per millimeter. A millimeter is the size if you were to take your thumb and forefinger and bring them together, and right before it appears that they touch, that little sliver of light, that's about a millimeter in distance. So try and think of 600 lines in that space of a millimeter between your thumb and forefinger right before they appear the skin is touching. If I take a laser light and just shine it on an opposite wall, you'll see a single dot. If I pass laser light through a diffraction grating, depending on how many lines per millimeter have been cut into it, that laser light will spread out. Essentially what diffraction means, to spread out. So here we see different lengths. This is the width of these slits in the diffraction grating. You see the diffraction varies depending on the width of that opening. So sunlight is an example of what is considered white light. When a ray of sunlight is diffracted, Sir Isaac Newton first accomplished in 1666 using a prism, you can see what Newton described as the color spectrum. And spectrum is right up here for you for the spelling, spectrum. So with a laser, you have very singular diffraction because the laser's in one color. If you take white light and you pass that through a prism, you end up with colors, the individual colors. And the order of the colors is dependent on the way in which the light is refracted, so appears to slow down or change direction as it exits here. And so the very specific frequencies of light will determine how you perceive them in which order. Red has the longest wavelength and the blue's the highest wavelength. So you'll always see the red, orange, yellow, green, blue, indigo, and violet. This is representing what Newton did in 1666, or this is representing a famous album cover. Some of you might be familiar with Pink Floyd, Dark Side of the Moon. Maybe Dark Side of the Moon. Keep it in the prism form. Truly the dark side. It's the best side of the moon if you ask me. Mention Pink Floyd's, you gotta mention Pink Droid. This is a very classic image for artists to play with, the concept of white light being broken down into the various colors. Chalk and crayons. If you're in the classroom, this is similar to how I would do it. I would take a clear container of water and I'd put it on this thing known as an overhead projector, and we would cast not one, but 4 color spectrums throughout all the areas, corners of the classroom for you. You'll be glad you're not in the classroom, because then people aren't going to burst into song such as the following. Feel free to sing along at any point. Here's another rendering of this spectral color spectrum image. Very painstakingly done with the embroidery floss through the eye of a needle. You say they switch the orange and the yellow there, though. Alright, so these circles here, you can color them in, or you can just write the names of the colors here. On this side, we have the primary colors of light. This side, the primary pigment colors. 2 very different views of color. The first one here, primary colors of light. The primary colors of light are red, green, and blue. You can press pause as you color or write those names in. These are pronounced cyan, magenta. And the key principle here is to recognize that if I have equal parts of red light, blue light, and green light, equal parts of those 3 primary colors of light are going to give me white light. It's kind of reverse thinking about taking the white light, passing it through a prism, and getting the colors. Here's taking the 3 primary colors of light, red, green, and blue, mixing them in equal parts, and getting white light. This is how television screens, computer monitors work. Probably more so rectangles side by side for you. But what the television or the monitor is designed to do is to take information from the streaming service you may have of what percent of light energy to shine on those little different tiny cells. Well, you'll have a red, green, and blue rectangle right next to each other and just continuous across the screen in rows and columns. For example, if you want to get this particular gold or yellowy color, then your television monitor or computer screen is going to receive the message of 100% red and green, but no blue. And that's essentially how any type of interface of light, we get all the different colors. You don't have to have a light bulb or LED in every single color to produce all the colors on your monitor. It's just the various percents of red, blue, and green. Here we have the primary pigment colors, what you probably think of when you think of colors. Those things dealing with paints, pigments, dyes, oils, acrylics. The primary pigment colors are cyan, yellow, and magenta. You can pause to jot those down, that when you mix cyan, magenta, and yellow in equal parts, you get black. And you also get, notice, the secondary pigment colors, which happen to also be the primary colors of light. Keeping with our dark side theme here, equal parts, you end up with the dark side. Again, if we were in class, I'd demonstrate this for you, but here's a video clip. So having blue light shine on this practice golf ball, then the green light and the red light, and you'll see white. And you'll also see the primary pigment colors, which are actually your light secondary colors. So the secondary colors of light here. But the key principle is to understand red in equal amounts, blue in equal amounts, and green in equal amounts of light give you white light. All right, why go over all this coloration in the world of astronomy? Well, that's coming up here shortly. First of all, we're going to have you describe the 4-color printing process used by printers and newspapers, like maybe the Daily Planet. So if you've ever changed the color cartridges in your color printer, if you should happen to have one, you open up the covering and you don't have 256 million different cartridges, as the eye generally can perceive about 256 million hues, they say. You only have 4 cartridges, hence the 4-color print process. You have a cyan, yellow, magenta cartridge, each of those being a primary pigment color, and black. And the black is used for shading and enhancement of color pictures or obviously black text. If you've ever looked close up at a magazine or a comic and you zoom in, you'll notice it's just a different saturation level or overlapping of cyan, yellow, and magenta to produce all the different colors. These are some coasters of the Mona Lisa that I have, and they are each in the primary colors of pigment and the black, so the 4-color print process represented. And what I like to do is demonstrate how it doesn't matter the order that you stack these on one another, they will always produce the Mona Lisa in all the different hues and shade. So no matter the color orientation and way you stack them, you'll get the same output. So when you're operating your color printer, it's laying down a certain saturation level of the cyan, the yellow, magenta, and of course polishing off with the black. Printer black ink is more expensive than human blood. I'm not telling you to pour blood into your printers thinking that you're saving money. This is one of those things about perspective. If you go into a store and think about how much you pay for a gallon of milk versus, say, a gallon of gasoline, or a gallon of butter, a gallon of peanut oil, everything seems a little bit crazy when you think of it in one considerate unit of, say, a gallon per. So in that regard, human blood is actually less expensive. But of course, you can't quite put a price on blood that can save human lives. So the color spectrum, why are we looking at this in terms of astronomy? Well, this visible light, this is what we've been looking at in showing you little dots and blips on night skies, showing you asterisms, constellations, but we haven't been showing you the whole ball game. It would be quite frustrating if you only learned what was going on from a baseball game if you were seated along the third row or third base line. You wouldn't get a full sense of what was going on with the game. You want to definitely see not just what's happening along the third baseline, but the entire game. And that's the analogy for the electromagnetic spectrum. We've been showing you just one portion of things from the cosmos, but they're also emitting all other types of radiation levels. And we can see a much fuller image of a Crab nebula, the Crab Nebula. Nebula is an interstellar cloud. We can see there's a lot of energy happening in infrared, heat energy. There's so much more to explore. So instead of just watching the third baseline of the game, we want to see the entire game. And we showed you the way in which color is processed because that's how photographs are processed. Your satellites will send back images telling a graphic designer, a computer artist, to put in this amount of red, green, and blue to form a composite image. And sometimes these are called false color images, where sometimes we want to recognize a particular type of radiation. Like maybe we want to enhance infrared. So maybe here we say, okay, make the purple infrared, for example. And so that gets the term a false color image. Give you a little rundown of how satellites take data to then turn into pictures for us to enjoy. When a satellite observes an object in space, its camera records photons, bundles of energy. These photons come down to Earth coded as values in the forms of ones and zeros. Many of you know that's binary code. The scientific software then translates this data into a table that contains the time, energy, and position of each photon that struck the detector during the observation, so the intensity. The data are further processed with specialized software to transfer the columns and rows of information into a visual representation of the data. You get this image, which is in black and white. Colors, as mentioned, play a very important role in communicating information in astronomical images. Sometimes colors are chosen to illustrate specific bands of light. There can be other motivating factors when picking colors, such as highlighting a particular feature or showcasing particular chemical elements. The end product is not only visually pleasing, we would hope, it also offers a lot of information. This image of the Crab Nebula remains of a star that exploded over 1,000 years ago, demonstrates the possibilities of seeing our universe more fully thanks to modern technology. In this image, the blue represents the X-ray frequencies, red and yellow represent the visible light portions, and purple represents the infrared. So you can get a lot of information from the data the satellites are sending us. So this would be called a false color image. False color in that we've purposely said, okay, infrared, let's shade that purple. Hence this little comic by Sidney Harris. The astronomer has his portrait painted in false colors. So we wanted you to be familiar with these other forms of energy besides light energy so that you can fully appreciate as we start to move now into the course of showing you images from other space telescopes, such as the very famous Hubble Space Telescope. This is just looking down the third baseline or visible light. which is wonderful and gorgeous. But astronomers can attain a whole nother level of information with looking at infrared frequencies. Again, just showing you the differences of infrared versus visible frequencies. There's so much more to uncover in these different frequency ranges. The space telescopes don't always have to be put out into space orbiting our planet and concentrating on the portion of the cosmos that they are detecting and collecting data from. We can have airplanes that can be adapted, modified, and become an observatory. This airplane is the Sofia Project, as you can see there, the Stratospheric Observatory for Infrared Astronomy. So it's a joint project between, you see, the countries of the US and Germany. And this is designed to focus on infrared frequencies or energy. And the plane climbs much higher than commercial flights, well above the 30,000 feet of commercial airlines. It gets into the stratosphere levels. Once at the altitude that provides the plane to be in what we call a geosynchronous orbit, so it's moving in time with the Earth, so it can lock onto a still image, you will have this hatch open up, and here is the telescope that is designed to gather the data of what it's focused on in the infrared frequencies. A Star Trek original cast member you're probably not familiar with, but this is Nichelle Nichols. There she was as the original Lieutenant Uhura. She was invited to participate in one of the Sofia projects. So the front half of the plane you'll see is the computer systems. Here's the telescope area. And then of course over on this side you'd have your pilots. Nichelle Nichols came to Salt Lake in 2015. She was originally a Broadway star, so she always likes to sing when she's at these fan experiences. And let's show you some of the striking results of the fabulous Sofia telescope. Here's our lovely go-to Orion star pattern. And this is in the visible light range, what we've been showing you pretty much all trimester. And through Sofia, here's the infrared information. So we can tell these are very large stars right here. Just so much energy, so much more to be understood than just looking at the visible range. We do have space-based telescopes, meaning telescopes that are beyond our atmosphere, so we don't have to worry about the atmosphere diffracting or refracting light, causing problems with the imagery. We can put them into our above our atmosphere into space. And note that this is flipped around. Normally I print radio on this left side, so you can think of L, left, long radio waves, lower energy. But this one's flipped around, the high energy here to the low. And these are all telescopes. You've probably heard of HST, the Hubble Space Telescope. It will take images in visible light. It also has capability to do some infrared and UV, but primarily the visible light. And then this radio telescope, this satellite dish, this is ground-based. This would be one in the picture that's not outside of our atmosphere. And the last portion of the course deals primarily with radio astronomy. Here's the color image. It was a little cheaper to remove the black and not use so much toner as we printed your notebooks. And don't worry, every frequency is covered by various telescopes. Just another visualization. Sofia doesn't fly quite that high. It's not necessarily orbiting the planet, but it is above the Earth's, above the typical flight pattern of airplanes. And from all these telescopes, we're able to get so much information about our solar system. It's just absolutely incredible what images these particular spacecraft have provided. And so you don't lose any sleep at night. There's always crossovers. We have every frequency of radiation being taken in by these space telescopes. And these being the space telescopes themselves. Here's the Hubble Space Telescope, the Chandra X-ray Telescope, COBE's, a satellite we'll talk about a little bit later in the class. So, putting everything together and thinking about what we've learned, images that you see from space are composite images. This galaxy is an image produced by the infrared imagery from the Spitzer telescope. The X-ray imagery produced from Chandra, those are overlaid with the information gathered from visible light of the Hubble. So much information within the various energy levels or frequencies of that EM spectrum. Looking through the arm of our Milky Way, the band of our Milky Way, in the different frequencies. And this is a great website that if you go to, you can click down the side as to which type of radiation you want to see the imagery for. So it's nice and interactive rather than this still photo. Highly recommend that website for you to go to.